Right, so for the next talk, we'll see Let Generalization by Joseph. Please go ahead.
Research on Let Generalization, Polymorphic Recursion, and Variable Minimization in Boolean-kinded type systems. So a Boolean kind is a Boolean algebra at the type level, and we extend Hindley-Milner with Boolean kinds to facilitate fine-grained type inference for a variety of properties and features. Our running example will be nullable reference types, and the problem that we're solving will make more sense once we see the example. So nref is a type constructor. Its kind is ml to bool to ml. ML is just the normal, regular HM kind. Bool is a new kind that we're adding, and its inhabitants are 0 and 1. Okay. If nref binds a 0, it means that that is the type of a nullable reference. If nref binds a 1, that is the type of a non-null reference. Okay, so we introduce some operators, make reference. Alphas are ML variables, omegas are Boolean-kinded variables. Okay, and we have omega b. We have omega b we have nref bind an omega instead of a 1 because we want to allow omega to instantiate to being a 0 or a 1 as needed, because we can always use a we can always use a non-null reference as though it's nullable. Okay, so we have null reference, and we have operations for reading and writing references, right? We enforce that the reference being, that we're reading or that we're writing to is non-null. That makes it safe. All uses of the signature are safe. You can add an unsafe, operator if you want. And so far, everything is syntactic. So everything so far can actually be checked with like syntactic unification. Okay, so we make some space, and we introduce some new operators. First one is no coalescing. Okay, R1 coalesce with R2. If R1 is null, we return the right reference. Okay, the result is non-null if either input reference is non-null, and we could express that relationship right in the type using the Boolean connective. Okay, we can introduce a bind operator that has the opposite relationship. Okay, so let's walk through an example. What is the type of wand? We are dereferencing R1 coalesced with R2. So if you think about this example, if the left reference is nullable, right reference better be non-null. If the right reference is nullable, left reference better be non-null to guarantee that we can always extract the contents. So we have this one stuck case, and we need a principal type that can somehow express the interdependence between the nullabilities of these two references. Okay, so let's walk through type inference. Okay, so in classic HM fashion, we have that the argument to the dereferencing operator is equal to, that type is equal to the type of the result of no coalescing. That creates a type equation. Okay, injectivity of syntax, we get two subproblems. Right, we use syntactic unification to solve the syntactic problem. We use Boolean unification to solve the Boolean problem. Okay, and we can get our principal type that expresses the relationship between the nullabilities. Okay, so to reiterate, we can use Boolean kinds to track properties. We could have Robinson unification defer to an equational unification algorithm for type inference. Okay, set algebras are also Boolean algebras. So, for example, take this record system from Kennedy. We can use we model or we type records as sets, and so record concatenation sort of has this relationship with union at the type level. Okay, so property tracking corresponds to Boolean algebra over 2. Width typing corresponds to powers of 2, and there's real research being done recently by the Flix, by Flix researchers who use Boolean-kinded types in their design of the Flix programming language, right? And particularly important is the recent work on qualified types, which sort of condenses a lot of previous work on type-level properties. It's pretty nifty. Okay, so past work has subsisted on Boolean unification to support basic type inference. Okay, but we might want to do more. For example, let generalization was open. So in this presentation, we'll develop methods for local let generalization, polymorphic recursion, and variable minimization. Okay, and this has some clear benefits: code reuse, expressivity, readability. Okay, so we use Boolean ring formalism. Okay, so plus is exclusive or symmetric difference. Multiplication is and or intersection. Okay, the Boolean kind forms a ring over the associated operators, the relevant operators. The important thing is just that anything plus itself is 0 because we're working mod 2 essentially. B denotes complete axiomatization of a Boolean ring. Okay, so polynomial form is a canonical form. What this means is that if two types, okay, row 1 and row 2, are equal up to axioms, we can normalize both of them to some row 1 tilde, row 2 tilde. And they'll be equal syntactically. If row 1 and row 2 are not equal up to axioms, they won't be equal syntactically, right, after we normalize them. Okay, polynomial form is more commonly called ANF. Okay, so it's rather clear that omega occurs syntactically in omega plus omega, but does omega occur up to axioms? Well, in order for it to occur up to axioms, it has to occur syntactically in all equal types. So in this case, omega plus omega reduces to 0. So we do not say that omega occurs in omega plus omega up to axioms. Okay. So in general, the variables which occur in polynomial form syntactically are exactly those which occur in the type, right? And there's a proof by contradiction. It just relies on this fact that normalization, that we have a normalization algorithm does not introduce new variables. Okay, so now does omega 2 Boolean occur in the type scheme for omega 1 plus omega 2? This is a more interesting question. We're getting closer to the research. Okay, so the answer is, well, type schemes are equivalent if they're instances of each other, right? So if there's instantiations on the rank 1 variables that allow you to go back and forth. So we can say that, you know, the reference or the type scheme on the right is an instance of the type scheme on the left, and vice versa. Okay, so that we have that these type schemes are equivalent. They're instances of each other. And so we can say that omega 2 does not occur, right, in the original type scheme because it doesn't occur in the highlighted type scheme. Okay. And so, yeah, so omega 2 is not a free type variable, if it, you know, in the context of a type system. So we normalize type schemes such that all unquantified variables occur up to type scheme equivalence. So the idea here is that we're going to be computing eliminators, right, on quantified variables. We call those rank 1 variables. We're going to be computing eliminators on rank 1 variables that eliminate rank 0 variables. Okay. And we're going to work over collections of types, right? So in this example, we have two nrefs. Those each bind nullabilities. Those are shared. Those are under a single quantifier, right? That omega 1 is shared. So we have to operate over collections. Okay. So what is elimination? Well, an E-eliminator eliminates, right, the dependency of a particular variable from a collection of types. Right? So in this case, you know, if you focus on the right, epsilon is eliminating the dependency on omega, but it cannot actually instantiate or replace omega directly. So you have to use, you know, nilpotence or item, you know, you have to use these different, you know, like annihilation, you know, to sort of be able to eliminate the dependency. Okay, and there's a reduction from Boolean elimination to unification from past work. Okay, and we care about this idea of preservation. So if we apply a substitution sigma or some instantiation, there's an instantiation on rank 1 variables back. So we say that it preserves the let generality. A substitution preserves the let generality if it doesn't actually change what the scheme is up to equivalence. Okay. So again, we are going to compute eliminators, right, on rank 1 variables of rank 0 variables, and we're only going to keep those that preserve equivalence. Okay, and so to normalize, we just repeat this process for all of the rank 0 variables until we're left with only the ones that are essential. Okay, order doesn't matter because everything is equal up to type scheme equivalence. So we can compute free type variables. We're halfway there for local let generalization. Okay, there's a second problem. See this context, we have omega 1 plus omega 2, right, as a nullability, and we have this typing. Okay, omega 1 and omega 2 both really occur in gamma. Okay, but we can apply this substitution. Okay, that substitution introduces this omega hat. The omega hats cancel in gamma, okay, but not in y. And so that's a new free type variable. Okay, we can form a type scheme around that. Okay, and that produces a more general type. Okay, so what do we have to do? We have to apply a substitution which reveals the polymorphism hidden in the context, right? And it turns out that there's always like a substitution which reveals the maximum amount of polymorphism, right? So we'll be able to have completeness. Okay, the problem is roughly that there are these extra derivations coming that are a consequence of the self matches on the context. Okay, and so we'll construct a substitution gamma which parameterizes these self matches on fresh type variables, right? And the new fresh type variables will form type schemes because they can't appear in the context because it's a self match. Okay, so basically what's going to happen is we're solving the self match context equation using something called Levenheim's method. Okay, so when the guard holds in this construction, gamma is going to be our B generalizer. Gamma is going to equal some renaming, some freshening operation when the guard holds. It's going to be identity when it doesn't hold, and that's able to parameterize a set of self-matches if you imagine new bar as like some arbitrary instance of some uninstantiated omega bar. Okay, so we show how to construct type inference with the required semantics in the paper, more details there. Okay, formally, a E generalizer gamma obeys this criterion, which was specified by Kennedy in past work. If and only if two substitutions have the same effect on the context, there exists a way to extend sigma 2 into sigma 1, so to speak. There exists this extension eta, which makes it so that the entire right-hand side is sigma 1. And of course, if sigma 1 and sigma 2 do not have the same effect, then that extension cannot exist. So in our case, sigma 2 union epsilon will distribute sort of elegantly into our little gamma, okay? And to show that this works, we'll prove the forward direction in its inverse. Okay, if sigma 1 and sigma 2 have the same effect on the context, we can fix eta as shown. Then the guard always holds, and we'll have that the entire right-hand side reduces to sigma 1 because the if-then-else term will go to the true branch. Okay, if they have different effects on the context, okay, well, the if-then-else is going to be forced into the else part, okay? And since sigma 1 and sigma 2 have different effects on gamma, they must have different effects on the free type variables contained in gamma. Okay, so at this point, we can perform local let generalization, okay? You just do type scheme formation as normal after you apply gamma. And the next topic of interest is polymorphic recursion, right? Giving recursive calls access to their own type scheme. So we can define a list type as shown. Just the idea here is that if nlist binds E0, it means that all references are presumed nullable, but if it binds a 1, there must be a non-null reference somewhere in the list. Okay, the destructor must reflect, so there's sort of a gap between the constructor and the destructor. We can't presume to know whether or not it's the head or the tail that contains the non-null reference, so the destructor has this existential component to it. Find ref, we can define this iterated version of the no coalescing operator, and then we can just have this iterated version of the wand example that we started from. By the way, the wand, that name comes from the literature on record concatenation, and you could sort of adapt the problem there to nullable references. Okay, so we have this iterated version of the wand example, and we expect to be able to define these types, right? So if nlist binds a 1, there's a non-null reference somewhere in the list. So if we coalesce the whole list, right, we should be able to extract the contents. Okay, but it turns out that polymorphic recursion is necessary for the type of find ref and the type of deref list by consequence. So we annotate some types. In classic HM fashion, the type of the recursive call is equal to the type of the function body or the function definition. That creates this equation. This equation forces nlist to bind to 0, so we can't really presume anything. Okay, but it turns out that that is more, that's more special than we need. It just needs to be the case that the recursive call is more special than the type of the recursive definition, because we could always use a function in a more special way. Okay, that's the idea of let generalization. So in fact, we just need to apply a substitution such that the square subset equal, which says that the left is an instance of the right, such that that holds. Okay, and so it suffices to satisfy, right, this relation, as already stated. And in fact, there's a sense in which polymorphic recursion is actually a generalization of let generalization, right? If you have a sequence of like let expressions, right? Since polymorphic recursion is giving recursive calls access to their own type scheme, right? In a recursive block, each recursive call has access to all the type schemes in the sequence. Okay. So in general polymorphic recursion, in general polymorphically recursive type inference corresponds to solving semiunification problems. Syntactic semiunification is notoriously unsolvable. Boolean semiunification is solvable essentially for the same reason that SAT is. The satisfaction problem. Okay, so again, we have to solve over collections. And Boolean semiunification is readily amenable to Baz's method, which is a semiunification strategy with termination dependent on E. So justification is split into 3 parts. The first 2 points are sort of generic over E. The third is more specific. Okay, so we have Boolean semiunification on the left. We have Baz's problem on the right. I guess the German is more like Bots, but okay. If we look at this, we can very quickly see that that every solution to the semiunification problem must be a solution to Baz's problem, because that sigma tilde on the right-hand side of the B semiunification, that can just be a part of the residual substitution that's being hidden by that square subset equal operator on the right. Okay, so every semi-unifier is a solution to Baz's problem. That means that the most general solution to Baz's problem must encompass all of the semi-unification problems, right? And that means that we can repeatedly, we can always solve Baz's problem on a semi-unification system without losing any solutions, right? It's always going to be a superset of the solutions that we get out there. Okay, so now we have Baz's problem on the left. We have B unification on the right. We need a way to implement Baz's problem. How do we actually solve this problem? Well, if you look at it, we have, for Baz's problem, we have the sigma on the left-hand side. We have a residual substitution being hidden on the right-hand side. That looks a lot like unification. And in fact, if you just rename the omegas on the right-hand side to some new bar, it is unification. And you can prove it formally, but I think it's easy to see intuitively. The problems are equivalent, so we can use B unification, Boolean unification, as a way to solve Baz's problem. Okay, and an equation is solved, meaning that, right, so the semi-unifier is the identity function, so there just exists a match. An inequation is solved exactly when a most general solution to Baz's problem preserves the left-hand side of, like, the system. Okay, and so to see this, if the inequation is solved, we can just say that all solutions to the semi-unification problem are solution to Baz's problem, so we just say sigma equals identity, and therefore all most general solutions must be equivalent to an identity. Okay, if we go the other way, assume that the solution preserves the left-hand side, then we can see that the inequation must be solved, because if you just follow the arrows, it's mu sigma dagger. Okay, so there exists a match already. We invert both sides, and we can say that if we solve an unsolved equation, it must irreversibly narrow the left-hand side of, or you could just say that it must narrow the semi-unification system in some way. Okay, Boolean rings are finite. There's only a finite number of proper instances of any formula, so Baz's method must terminate. And this even works, this is even true for infinite Boolean rings due to their special structure. Okay, so we may now solve a system of inequations, and that means we can do polymorphically recursive type inference confined to the Boolean kinds. Okay, the last problem that we study is variable minimization. Okay, and so take this example. What is inferred type? Well, it's this type following our methodology, but there's a better type. That's a better type since the references to 0 and 1 don't appear, we're not using them in any other way. They're confined by their scope to that expression. We don't need to separate omega 1s and omega 2s. We can just map them to some omega. Okay. Similarly, there are situations where, depending on what Boolean unification procedure you pick, you could get solutions of varying quality. Right? We might want to equalize, right, these different solutions. That's another application. So we'll solve the problem over collections, and then that can be extended to solutions over substitutions or contexts. That's all in the paper. Okay, so minimization basically amounts to trying to group like dependencies together behind some binary function phi. Okay, and once you've done that, it's very easy to compute the match from the left-hand side to the right-hand side due to the strict functional completeness of the Boolean algebra. That match must always exist, and that allows you to compute something that we'll call a one minimizer, which decreases the number of variables in the collection by 1. Okay, and so we can reduce the computation of one minimizers to Boolean unification. It's just like a bunch of math. Okay, and so on the left-hand side we have the original. We have our original collection. On the right-hand side we have a new collection, and we have a phi binary function. Those are just like fully polymorphic. Those are just encoded using unification variables. And so we just solve and we ground the extra variables. Okay, and the one minimizer is the solution to this matching problem. Okay, so we repeat this process for all variables, for all pairs of variables. And so if we have the B minimizer, like the full minimizer on the left, we can introduce this family of involutions, and we can degrade the B minimizer into a one minimizer by just making it worse and worse by having it introduce more and more variables. And so it's very easy to see that the B minimizer must be constructed out of one minimizers, and so there ends up being a way to inductively build it up. And so it suffices to just to compute it for all pairs, and you have to try all pairs. As it turns out, but fortunately the order is not important as everything is equal up to equivalence. Okay, so for implementation we provide standalone implementations of all three procedures in OCaml. We also provide a reference implementation for an ML dialect which supports nullable reference types with local let generalization and polymorphically recursive type inference. Of course, the solutions of the paper generalizes to any Boolean-kinded system. Additionally, provide proof sketches for syntactic soundness as well as the correctness and completeness of type inference for nullable reference types in case there's any interest there. Okay, so in summary, we solve problems in type inference by procuring procedures for the corresponding problems in automated reasoning. Here's a table. There's this nice correspondence. And for future work, you can consider like more correspondences. You can consider other equational theories, right? Other algebras. You can consider new applications of Boolean-kinded types, so on and so forth. And that's my time.
Thank you. Yep, you have questions?
Thank you for the talk. I'm curious if have you considered sort of, so you mentioned here the language features, sort of considering other algebras. I feel like Boolean algebra is a relatively rich structure. You have negations, for instance, and I wonder if you've considered what happens if you, for instance, only have a lattice? Do things get simpler, or maybe do they get harder?
They get way worse. So not every algebra has most general unifiers, right? We're sort of blessed with most general unifiers for syntactic unification, Boolean unification, abelian group unification, right? Some generalizations of Boolean group unification. Then there's some more obscure stuff like if you just have left or right-sided distributivity. But most theories do not have. Most theories just do not have most general unifiers, and so then there's a burden of type annotation, and of course complexity, it varies wildly as well, right?
Cool. I'll actually ask a similar question to the question I asked before as well. Mm-hmm. What did you think of the user signatures that you get in this sort of system? I don't know, you say you have an implementation, but I don't know if you looked at sort of some specific, if you try to inferring types for a specific program, so you had some benchmark.
Yeah. So if you want, like the Flix programming language has like way more evolved, they implement, at least at some point, they implemented some version of their nullable references system. And so if you want to see like real world nullable or real world Boolean kind of types, you should see what they're doing over at Flix. It's really nifty. But yes, there is an implementation, and I think we must show some types in the paper to some extent. Like you saw the type of the wand example. Yeah, it's at the very least there's an implementation, and you could definitely check that.
Thanks.
Okay. Next speaker, please set up your computer. And there's a last question, online question, which is: Are you planning to apply this work to Flix or some other experimental programming language?
So far there's not really any plans. The Flix people at the moment have a limited amount of time, and they're like ideologically opposed to let generalization. But who knows? It's yeah. So far no plans, but I might continue to develop my current implementation to something more evolved. Who knows?
Okay, great. Thanks. Let's.